Hello everyone, today we're going to go through SJPO 2013 special round question 3. A card of mass m has a pole on it from which a ball of mass mu hangs from a thin string attached at point P. So it's going to look something like this. The card and ball have an initial velocity v. The card crashes into another stationary card of mass m and sticks to it. So this is a completely inelastic collision. You already know that maybe we can analyze some momentum, right? Conservation of momentum. And if the length of the string is going to be r, show that the initial smallest velocity for which the ball can go around in circles around point P is of this form, where A and B are constants, and you have to determine that G is the gravitational acceleration, neglect friction, and assume that both m and m are much greater than mu. Okay, so we know that this question is actually in two parts. One is definitely going to be momentum. You want to find the velocity using conservation of momentum. But the other part is about circular motion. What exactly about circular motion? Let's try to model what happens when this system collides first. This whole thing, moving at v, this whole system here, is going to collide with this. And because it collides with this and this is stationary, the whole system velocity will decrease. Both this card and this string is rigid, meaning that its velocity will instantaneously decrease. But this string here that I'm highlighting is not rigid, meaning that for that moment, its velocity is still going to be the original. So what we have here is this ball of mass mu. It's going to move at a speed v when all the other things is going to move at a speed vf that is less than v. So, meaning that we have some difference in velocity that will allow it to complete this circular motion. It's about the net velocity of this ball. So, what as and of course, as this useful result that will help us here, the minimum velocity at the top of a circular motion is going to be root rg. The minimum velocity at the bottom of a circular motion is going to be root phi rg if you want to complete this circular motion. So, but of course we are going to show how to derive this, but if you have this memorized already, you'll notice that this root phi rg is very similar to what the question wants, which is alpha gr to the power of b, because it's simply phi gr to the power of 1/2, so you know you're onto something. Let's derive this equation for minimum velocity at the bottom, because that's what we know we want to find. Okay, so let's start. So we have to start with finding the minimum velocity at the top. So when we have a circular motion here, and say a ball here, it's going to have its mass mg, it's going to have normal contact force or tension N, and the centripetal force or net force is mv squared over r. When we do the force analysis, we find that at mg minus n is mv squared over r, meaning that mg plus mv squared over r is going to be equal to n. So what we want is we want v to decrease. Mg remains constant. So we want v to decrease to the point where n decreases all the way until n hits 0. Because when n hits 0, it is the minimum velocity where it's going to continue the circular motion. If n is less than 0, I'm going to fall into a projectile motion already. It's not going to be a circular motion. So we can sub n equals to 0, and we'll actually find that mg equals mv squared over r, gr is v squared, v is root rg. So this is going to be the minimum velocity at the top to continue circular motion. And of course, this is a tangential velocity. So how do we find the v minimum at the bottom? We'll just use conservation of energy. This is going to be r, and we can basically write that your Ke at the bottom plus GPE at the bottom is going to be Ke at the top plus GPE at the top. Ke at the bottom is going to be half mvb squared plus 0 is half m v squared, because v squared is going to be rg. We can replace it with rg plus GPE at the top, which is mg2r. Multiply everything by 2. Get mvb squared is mrg plus 4 mrg. Cancel the mvb squared is phi rg. vb is going to be root phi rg. So your minimum velocity at the bottom if you want to complete the circular motion. Okay, next we need to analyze these velocities, because we want to find that your v minus v final, which is going to be the relative velocity of your mass mu. We're going to have to make this root phi rg. But of course we have to find v final first. So we can use conservation of momentum, which is very standard. Right? Pf is going to be pi. Pf is m plus m vf is going to be, and pi is going to be mv. You can find that vf is simply m over m plus m times v. Right, so vf is going to be lesser. We have v minus vf is going to be root phi rg. So we can just sub it in. M plus m phi rg. So v1 minus m over m plus m equals root phi rg. Okay, we have reached a very important equation. And keep in mind that this is going to be v minimum. It's your minimum velocity that this cut with mass m needs to have. Right, so we can already find this, your v. Let me just copy and paste the equation. So we have this equation here. You can already find your v minimum, which is simply m plus m for m times root phi rg, which is very, very similar to this form they want us, which is 1 plus m over m agrb, agr to the power of b, right? So this is simply, right, this m over m is just 1 plus m over m. Phi rg is just phi gr, because r is the radius, small r is simply big R, it's just the same thing. And b, this constant beta, is half because it's a square root. So we have found the equation for v minimum, right? And we can also find that alpha is phi, beta is half. We have solved this problem. Right, so here's the solution for question 3. Thank you.